Hello, everyone. Today we're going to talk about simulation-based inference. So first, let's talk about what is simulation and why we need a simulation-based inference. So simulation is a process that we are trying to model the real world. And in experiments or whatever researches, when they get lots of data, and which is kind of like random, we have lots of curves, lots of observations, and you may not necessarily want to refer to a chart or kind of refer to a chart if you want to do your engineering, and you may lots of times you want something like equation that if you just put the current condition into the equation and then you can predict whatever happens afterwards. So the process that we're creating these equations or these tools is called, that is the simulation. Such as this one, this is the cycling of harmony of three harmonies P, H, P, and G in the human body. And by tons of observations, we can get the relation that how the derivatives of these three harmonies changes, given that we can find out that, okay, so the H prime is proportional to 1 plus G to the N over divided by 1 and minus K1 times H. So yes, and obviously this derivative is somehow related to the current level of your G and H. So this kind of this is how your H harmony going to change for the next time, and same as P and G. But lots of cases, yeah. So this is quite useful. That means that whenever you know your current level of this harmony H, G, and P, you can predict what will be a harmony level for the next time, and which is super useful to your doctors to decide, okay, what medicine should I prescribe to my patient. But lots of times it would be very hard to kind of figure out what the specific parameters in these equations are. Usually what experimenters and scientists observe is this kind of curve that you somehow know that your equation is in this formula, but you need that specific parameters so that you will know, so that you can know how the system behave. So then, you can predict how the system behave in the future, and this is usually a very kind of painful moment, because you may need to try lots of parameters. And in this case, where you have 3 different harmonies and they are all kind of interplaying with each other, then your tasks become harder. So that is where simulation-based inference takes side. Is that simulation-based inference is that we try to do a Bayesian inference to predict the parameters we have here. And you may already find that, yeah, it's because these three harmonies just interplay with each other. It will be very hard for you to have a specific derivative of H prime and P prime G prime. Yeah, and it's kind of hard to, it will be very hard for you to kind of do a gradient descent, because your derivative simply depends on the other 2 ones. So for the cases that we cannot that we have the equation, that we have a simulation, but but kind of hard to do the gradient descent to predict, we can use simulation-based inference, which is basically the process that you are trying to estimate the probability that of your parameters given the current observation. So there are 3 labels in SBI. So usually you have your parameter of interest, which is this data, and you have your observation data, which is usually X. Yeah, and you have your latent variables. So latent variables is kind of what you see in your is what you see, what you can observe, the level of GPH, so the GP and H, yes, and you are trying to predict the K1, K2, and K3, which are the fixed parameters. So All right, and usually the process, is that you make the observation, such as you observe the graph here, and you try to think of like what could be the formula equals. So you have this formula, and then you can use simulation-based inference to get to try to test out, okay, what will be my parameters are, and then you will know that this function work. If it works, fine, we have our solution. And if it doesn't work, okay, we need to find another equation, which is kind of like quite common. So if we take a close at the function of SBI, so this is the base of SBI, which is the Bayesian inference. So if we want to predict that if we observe X, what will be the parameters theta? What we can do is that we can multiply. So the probability of parameter theta given X is going to be the probability that X of probability of X given theta times the range of theta divided by the probability of X. So in this case, this is our prior. And this is the parameter we want to, and this is the probability we want to get. What the SBI do is that, so what the SBI do is that you first propose that you have a distribution of your parameter theta. And what you are trying to do is that you are going to put your parameter theta into the simulator, so that you're going to generate lots of simulations. And with that, you can have the probability that given the probability of theta, you will have lots of probabilities that what will be my observation be given my parameter theta. Then what you are trying to do afterwards is that once you divided your so this is what you get here, that if you have your probability of theta, what will be my probability of X? So, and once you get that, you just need to sample your. You just need to take samples from your observed distribution, and then you'll be able to find like what will be my theta, what will my parameter theta will be if given the observation of X. So that's the algorithm behind SBI. So this process can be done with so there are various ways to do this process. So one of the easiest ways is of course Monte Carlo. You just need to with Monte Carlo, you are trying to like take samples from your observation, and there are other ways that, but this is usually a very time-costing step. So there are other people thinking of like, okay, then we can have like other ways to try to kind of like get our distribution more efficiently. So yeah, so one of the ways will be SMPE, is that we're trying to learn the estimated. So rather than just kind of like save a sample of like what will be my distribution of X given theta, they created every time they take after they take samples from the after they take samples, try to estimate what will be my observation given parameter, they train a neural network so that we can have an estimation of how my parameters will change with the given observation. So that's how they use to get, and afterwards that's how they used to get, and afterwards that you can try to estimate how my parameters will be given the current observation of x0. So what I will say that yes, this one gives a better observation. Yeah, this one does give a better observation, better estimation of your parameters, and yeah, it's kind of like less, and this is also kind of also less time costly apparent if we compare it to the ABC, which is the Monte Carlo kind of like the Monte Carlo method, whether you try to accept or reject your observation. And I will say that there are still lots of like shortcomings that SBI will face recently. So first is the sample efficiency. So yes, S&P does, so this way does solve it, but yeah, it is still kind of like quite time costly. And but I would say the biggest challenge is the quality of inference. So if you do the process by yourself, you will find a big issue that you kind of like get a range. You kind of like get a range of your estimation. So you may kind of like, such as my real parameters is like 10. You may get an estimation that from 9.25 to kind of like 10.2, and the peak is not as 10. So why is that? The reason is that, still go back to this. So here you have a proposed distribution of your theta and the proposed distribution of and there's the current proposed distribution of your observation, but this is not the real case. This is kind of like this especially this here, your given parameter, the probability of your parameter isn't the real case with your observation. So given that this is wrong and leading to that, yes, this part is wrong, it will be hard to have your observation to be correct. And in fact, in the demonstration later, we will see that if we shrink our, so at the process that we train our estimation of x given theta, if we shrink the parameter, if we shrink the distribution of our proposed parameter in this step closer to our to the true parameter, we will have a better estimation of our results. Yeah. So I feel that one of the process that people try to do it is the SNLR, which is that they're trying to find the likelihood of theta will be. So I tried that method. It does give you a more accurate one, but still not much accurate, and it's very time costly, but it performs better. So let's see it afterwards. About the or you can download this download the so I think in this one they integrate like several popular methods of the SBI here. Yeah. So if you're interested, you can just check the website. They provide tutorials and examples. So, all right. So I think I'm going to show one of my I'm going to begin a new share of the training app down, which is the no. Yeah.
So Shulin, Chris has a comment that to make the screen bigger, you need to exit the Google meeting so that the side windows will go away. Or maybe there's a way to hide those anyway. Then people can see the bigger screen of your presentation. But if you have other people joined there as well, that's okay. I mean, unfortunately, this is how it ended up being today.
Okay. And yeah, but I think I will begin on the demonstration of how to use the SBI. So derivatives, which is what you see in my slide 2, the derivative of the parameters. So, and you need to define a simulator, which is kind of like how you can get a different, which is like how you can get the output given the parameters. So here just like write down how if I have the derivative, then I just update my data so that I can get the trajectory of my observation, HP and G, and the trajectory is going to be my observation. So I suppose that the real observation. So I suppose that the real parameter, the accurate parameter is going to be 0.2, 0.3, 0.5, and I just compare the trajectory. So yeah, because SBI, I thought that SBI can only take like a numerical yeah. So this unit 2. Yeah, I never use it. So yeah, because I find that SBI can only take like a limited number of outputs. So that's why I just like write a compare of this of the output data of the output trajectory with my with the desired trajectory. So yeah, so just kind of like basically summarizing all the mean squared error between the simulated trajectory and my real trajectory. So okay, so suppose that I have an observation which is I have an observation, and this so that this is going to be my observation, then the 0.2, 0.3, and the 0.5 is going to be my real data. What I need to do with SBI is that I need to so I first need to assign a prior. So basically this is that I suppose that my my parameters is going to follow the distribution of from 0.01 to 1, and following the normal distribution and following the uniform distribution. And then I just do the inference. So that's basically that I have the simulator, and I have the distribution of I have the possible distribution of my parameters. So basically that's a range that where my parameters is going to fall in, and I specify the inference method and number of simulation, and then run it. So this is kind of like quite time costly, and so this is just trying to train the distribution of observation given the parameters data. So and afterwards I have I'm trying to infer the distribution of my parameter given that I have the observation. So this is what we do here, is that we are going to draw this is that we are going to try to infer that I think that's the process like Monte Carlo, that we are trying to see like which parameters give us the best possibility that we have the observation we have, and you can see the results. So with a prior probability with a prior probability of with a prior distribution like this. So this is going to be the results that I inferred. Yeah, obviously you see that there's some kind of like a deviation from the accurate data with the distribution that I inferred. Yeah. So actually, I tried to like increase the number of simulations. Yeah, actually, it has some effect, but it doesn't work very well. It doesn't work very well, and the reason behind this is because that if we look at the slide, if we look at the yeah, so if we look at the position of the district, if we look at the proposition of the of our SBI, we are going to find that there's a P of theta here, and there's a P of theta here. So this comes from the case that this comes from the case that like if theta and x are like independent of each other. Yeah, this is what I think. But the case is that if P of theta, so if our prior is not accurate enough, there's going to be a big deviation of our it's going to be so so basically case that the reason that we cannot get an accurate inference of the parameter theta, I think it's not because that we didn't have a correct inference about the distribution of x given theta, but rather that we don't have the real distribution of the parameter. So basically, this section is too large. That's how I feel about it, and I do try something in my experiment is that rather than setting a prior of like 0.01 to 3, 0.01 to 1, I shrink it to 0.1 to 0.6, which is kind of like closer to my real parameters, and it actually looking better. So you can see that rather than have a big deviation in the inference, so if I shrink the range of the prior, so the result is actually much better. Yeah, so this is what I found, and there are other people and I think there's also other people discussing the importance of prior in the Bayesian inference. So it actually, it does matter. So and another algorithm that people trying to and there are other people who try to and there's another technique called the sequential neural likelihood that's basically trying to attack this problem. Is that I think that they do a retrain. They add a step that they add the distribution of so is that they retrain they do a step of like retrain the likelihood distribution on I think they do something kind of like how to update the distribution of x given theta, so that you can have a better estimation of your parameters. So I haven't looked at it very I just began on this technique, so I didn't do it very good. Sorry for that. And so for the applications in SBI, so the proposed application is going to be yes, we can and here's so the application is so far some applications in like particle physics and neuroscience. So I found like I think I read one of the papers in neuroscience is that they tried this the translate method on I'm trying to infer the parameter of that one's parameter based inference. And I read another one in astronomy. Is that they basically discuss that this can be used in astronomy, but they do observe that in some cases the inference is not accurate enough. So we still have. So sorry for that. This is not a very well prepared one, but okay. Yeah. We still have time, so I think I want to share one of the videos that I think is very well made. So I think this guy, Dr. Kyle Cramer, I think he's like he's like a very important investigator, researcher in this field. So I think I will share his video.
License any asset type in one single time. Try it free for 30 days. Start creating with Adobe Stock.
Did you ever stress about us having 3 kids?
No, it was always part of the plan.
Yeah, and before I share that, actually, any question for me? Okay, yeah, and here's the YouTube. Here there's into YouTube.
The original poster. It's good. Very happy to be here. I've been looking forward to this workshop for it's been a year or more since and it has kind of in preparation for it, thinking about interpretability and what I wanted to say, it has kind of shaped some of my thinking in the last year. So that's been fun. So some of you saw a talk that I gave here in the opening tutorial sessions. I have there's some commonality, but the main message of this talk is different. But there is this kind of connecting theme of simulation-based inference. So I'll talk about that some more, and then try to bring in these issues of interpretability and somehow why, from a scientific point of view, that's important, and what aspects of that very heavily overloaded word are we actually interested in? And then also I'm going to sort of frame a lot of this in the context of sort of experimental design and like the scientific method kind of at large. There we go. Now I'm having problems with the thing. Okay. Okay, so I just wanted to thank funding agencies. So a lot of the work that I'm doing is funded from the National Science Foundation, but we also have there's a large grant from the Bohr and Sloan Foundations that went to NYU, Berkeley, and the University of Washington, and that pushed on a lot of really cross-disciplinary.
Yes, that's not to yes. So someone asked the one in the neuroscience. I think rather than that, I actually want to I think I will share
research, and so.
Rather than that, I'm going to share one have like so they do have they do have this like website that they summarize the papers and reviews. This is the review I read. I feel like that's pretty good. And so I think I will share this one instead. So that's where you can find like the applications in kind of like lots of fields. If you want to have the inference, I feel that this is going to be a good one.
Oh, I definitely would like to thank the foundations for that, because it's certainly influenced by a lot of my trajectory in the last few years. And in terms of people, there's a lot of people, but it's just kind of a collection of collaborators that I've been working with in the last few years, and it's roughly half physicists, half either computer scientists or machine learning researchers or statisticians or applied mathematicians, and it's been very very fun after getting tenure and finding the Higgs boson. I wasn't quite sure what career was going to look like after that, but it's actually been like one of the funnest times of my academic career recently. Okay, so this is from the website for this long program, and I just wanted to highlight a few things. And I did this in the last talk as well, but it goes through this overview, and I like the overview a lot. And talks about using machine learning. One point is here is either from experiments or simulations. I think it's important to keep in mind that of the talks, some things are really you have a simulator, and you're just trying to understand what's going on inside of the simulator, and then other times you have real experimental data. There's the point that I think is easy to believe that machine learning is allowing us to interrogate high-dimensional complex data in ways that were not before possible. So that seems very natural. Then there are these other lines in here. It talks about, however, a lot of the use of machine learning and the physical sciences so far has been limited to low-hanging fruits, as they've mostly been focused on fitting pre-existing physical models to data. I'm not totally sure what was in mind with that sentence. I mean, I think lots of things could be in mind when whoever wrote that sentence originally, and I'm not going to disagree with it strongly, but I will. There's another context in which trying to do inference in the context of a pre-existing physical model is still very, very hard, and I wouldn't characterize as low-hanging fruit. Is that your sentence?
So I wrote that.
Yeah.
I had in mind what I have in mind. I will propose, but I propose that gets faster.
Okay. Perfect. Well, successful. Yeah, successful. No, it worked. But it is kind of useful because I think it's I mean, it does sound kind of right, but I think there's another way in which you'll see that a lot of the talks that we've had are you have molecular dynamics or something like that. That's the model, but trying to do inference is very hard, right? So, but there's this kind of futuristic version, which is a lot of what the last workshop was about, which is about trying to sort of learn the models themselves, try to learn physical principles underlying the data, and try to automate the sort of scientific process in general. So I'm going to actually talk about that a little bit. And then there's also this part that, scientists or physicists, would like to have models that are physically understandable. And that certainly motivates this workshop, which is about interpretability. And I mentioned some things like wanting to have symmetry,
Yeah, so this is my personal style. So, so the experimental data is basically the observation we talk about. And, basically, I think if you do research, then you definitely want to fit the parameters. It probably find difficulty that you want to fit the parameters with your model, but there are lots of cases that, but the parameters basically they have their physical meanings. So obviously you don't have a kind of a minus 300K Kelvin, because covering temperature, because temperature cannot go below 0K, and basically you may not get kind of some data that's too big for the parameter. So I feel like this. I feel like if you want to make that parameters has some physical meanings, so we can kind of constrain the distribution of our prior of the model of the prior of the parameters that we put in the model. That's hard.
Conservation laws, symmetries, and things like that. That's one type of property you would like the models to have, but there's other notions that you would like them to have, so for instance, that they're interpretable in some way. So the way that I'm going to try to talk about this a little bit is sort of take a big step back and think about we have a lot of successes and a lot of things to be very proud of. But if we take a big step back and think about the scientific process, writ large, where are we? Okay, and this is you Google scientific method. There's of the images you'll find, many of them are really simple circles. This one I think is a little bit more interesting because it's got a little bit more going on. But think about these different steps in terms of you're thinking of an interesting question, you're formulating hypotheses, developing testable predictions. Machine learning has a pretty hard time formulating hypotheses right now, right? This is a difficult part. This is humans are largely doing this, and actually a lot of these making the observations. Okay, sometimes you have labs that are kind of automated and that's turns into robots or something, but oftentimes that's done by humans. A lot of what's going on here is still very much done by humans. And then I think machine learning is really happening largely in the kind of after you've gathered some data, you're helping analyze it in some way. And so
so there's something I want to add here. I feel like instead of the shortcomings that we talked about before, that is time consuming and sometimes may not get the peak value, I feel like what's actually more important is that you formulate the right hypothesis hypothesis because I tried it on my project and I formulated the wrong hypothesis in the beginning, and it does return me a distribution, but it return me a distribution that is exactly as the prior. So yeah, so I feel like checking the correctness of your simulator is actually more important.
Come back to this at the end, but like part of what I want to say is that I think one of the reasons that it's important for machine learning to be interpretable is that as long as humans are like, machine learning might do much better, like black box machine learning method might do much better than humans for like one of these boxes. But if you can't interpret it, then you kind of can't continue the process, right? Right now, humans are sort of in charge of coming up with new hypotheses and trying to figure out what the next experiment that you're going to do to test it is. And until we have computers that can do that very well and algorithms that can do that very well, it's important for us to be able to interpret the results. So that's in some sense like the takeaway message of the talk. But this loop, there's different ways of talking about this loop. Here's one that David Bly and company show a lot, which is this sort of box loop where the idea is that you're sort of you have some knowledge and some questions, you're making some assumptions here written in terms of the graphical model, then you bring in some data, you discover some patterns in the data. Ajay showed us very nice examples of this with, like ozone and climate change and what the patterns were in the literature there. And then once you have that model, then you might want to sort of predict and explore in some way, criticize the model and go in some loop. And in some frameworks you can automate a little bit of this, but in the broader context, in a really open-ended sense, that's still humans are doing a lot of that. Another way that you can kind of frame like the scientific method is in this connection to reinforcement learning. So I think you've all seen the news about deep learning and deep reinforcement learning playing the game of Go at superhuman levels. This is sort of time of training some system and how good of a Go player it is, and sort of beating the best humans and then beating the best previously trained model from the DeepMind team. And this is definitely one of the places where deep learning does very well. And the analogy of reinforcement learning to the scientific method also makes it alluring that somehow we're going to have robot scientists out there, right? So let's just kind of dig into that a little bit. This is, here's like one of the typical like reinforcement learning things you get from Google, where you have some agent that takes some action, interacts with the environment, gets some sort of reward. There's some sort of, the state gets updated, and then you sit in this loop. And so that, in this case, could be the robot playing Go, like it decides where to put a piece on the board, and you interact with the environment, which is like your opponent, and then, everything kind of sits in a loop. In the scientific setting, the way that I would say it is, if I'm a human agent trying to do experiments, I need to decide what experiment I want to perform. That's the action that I'm going to take. My interaction with the environment is like actually, doing the experiment and gathering data. Once I've gathered that data, I need to interpret it, which to me is basically like doing statistical analysis. And now, and then my state gets updated, which you can think of as kind of a Bayesian update. Like I had a prior state of knowledge, I did this, and now I update my to a posterior, and then I sit in this loop, right? Okay. Now, so that's the way that that's going to be largely the way that I'm thinking of it. And so just in terms of notation, I'm going to think of sort of a forward model that's making predictions. So I have some theories, and I'm, largely thinking, scientific type theories, not just some kind of random black box model. So I have some scientific theory. It has some parameters of interest. That's what I'm calling theta. And based on those parameters of interest, the theory allows me to make predictions about what the data would look like. So I'm calling the data X. Now, if I'm actually doing real experiments, then there might be things like calibration constants that aren't properly known, or all sorts of other things that I don't really care about inferring, but they will change the distribution of the data. So those are these nuisance parameters I call nu. And inside of my simulator, there are lots of things that are going on that I might not have access to in my actual observation. So, and those are going to call those latent variables. So these are all these like microphysical states that are available to you in your simulator, but you don't see in real experiments. So that might be, some like if you're doing fluids, like you have some very fine-grained simulation what's going on, but then the observed data is just some kind of like column depth that you're measuring or something. Any of the number of things that might come up. So those are the latent variables Z. And now, given this observed data, I want to try to do inference on mainly on the parameters of interest. And the thing that's tying everything together is some statistical model that says the probability of the data, the latents given the parameters of interest and the nuisance parameters. And if you're super duper Bayesian, a lot of times like people will call these things also latents. For me, I like, as a scientist, I kind of like to separate them, because even if you're like very frequentist, like I don't know if the parameter of interest is like the mass of the Higgs boson. Like I don't know what the mass of the Higgs boson is before I found out. I don't know if the Higgs boson exists. It's hard, you know, I could try to come up with a prior on it. It's like, but it's definitely has a different nature to it. There's no previous data out there to help me inform what that parameter value is. But the latent variables are things that have like, in a frequentist sense, have a real, you know, sampling distribution associated.
Yeah. Okay, so someone asked like, did we actually implement this, or this is just high level sketch of an idea? Yeah. He wrote the review. He wrote the review of simulation based inference, and I think he published lots of data on it. He's kind of like he's a statistician or kind of a mathematician in New York University. So yep. Yeah. And I think he was like working with someone in particle physics. So they do publish a short kind of like they do publish a short paper. Yeah. A one-page paper. That's what I found. But so this idea, so this is yeah. So if you were talking about this this video, this slides here, so that's the basic process that we discussed about the SBI, that putting the parameter, train the distribution, that we train the observed data, the observer data X, or say the kind of like the distribution of what we can observe based on the parameter, which is kind of like a distribution of parameters. And then we can use this relation between the observation given the parameter to infer that if we do observe something, what's going to be the parameter. So yeah, so I don't know if that's kind of like answer something. Yeah, and I think I saw another one is that yeah, first time in the group recording session. So yeah, I will share it later.
To them. So the separation is more like if you want to.
Yeah. So any question with this step here? Okay, I think I will continue.
Play nicely with frequentists, but in the end, you of course you can just put a prior on those and work in baseline. So. Okay, so now the way that I'm going to frame this next bit is in terms of statistical decision theory. You can do it in a few different ways, but I'm just going to walk through this, quickly. But so what I'm thinking of is I've got states of nature. So capital theta is like the parameter space for my parameters theta. X is the space of my possible observations. And then I also have an action space, right? So this is what I'm going to take some action. And then I have a statistical model that's saying what the distribution of the data is given the parameters. I have a prior over those parameters, and then you introduce this idea of a decision rule. This is a map that says, given some data, I'm going to take some action, right? And that action is completely arbitrary. I mean, it's completely abstract at this point. So it could be like claim the discovery, like I see the data, I'm going to claim a discovery or not, right? Or it could be decide to build another particle accelerator, or don't, or something like that, right? Or build some other experiment. And that's actually a lot of the framing of what I'm going to be doing. Is this decision rule is going to be basically what experiment should I do next? The action is what experiment should I do? Then I have a loss function, which takes in the value for the parameter of nature and the action that I take, and it's going to give me some sort of loss or a utility if you want. And what's interesting there is whether or not that was a good action to take or not depends on the unknown state of nature, right? So this loss function is a little bit tricky. You can then think about that's for like a particular action. I can couple it with a decision rule and talk about the risk. So I think about, okay, well, if my data is being generated according to my statistical model, I'm going to evaluate the loss for that value of the parameter that I don't know. I'm going to use my decision rule. I'm going to stick my data into my decision rule. That's going to give me an action. I can take that action. So this expectation is the risk, right? Interesting. So this is a frequentist thing. It's a function of the unknown parameter. So you can't really optimize that because you don't know the true value of the parameters. You could search everywhere and have some kind of worst case scenario type of action. But if you're working with the risk, it's always going to be in this kind of frequentist version. If you come with a prior in hand, then I can talk about the Bayes risk, where I also take the expectation, averaging over what I think states of nature might be. And at that point, then I can really optimize over delta. Like I can think about a bunch of decision rules and find the decision rule that's going to minimize my Bayes risk. Right, but you can't do that if you don't have a prior, right? So yeah, I think this expected loss is where you have a posterior. Yeah. So this is what leads to generalized Bayes rules and things like that. But I think this is the okay. So
anyone have questions here? So basically so the x of theta is what we kind of what do we want? So this is what kind of what we want to have for the this is kind of what SBI gave us, and so I feel like this risk is kind of what's our inference parameter is gonna deviate from the real parameters, something like that.
Okay, so here's just some setup, and it's just kind of important to remember where the prior comes in and whichever. But okay, the main point here is that there's a very solid, clear statistical framework, and this is very similar to what's going on in our applications. Okay, so what is the thing that I want to optimize? Well, it could be, the GDP of the country, or my personal happiness, or any of a number of things that I want to, as my utility that I'd like to optimize. If you're thinking of it in a very scientific way, maybe what you want to do, and this would be if, experiments were free and things like that, maybe what you would want to do is choose the experiment that's going to lead to the biggest change from your prior distribution on the parameter to your posterior. Hopefully, if you get some data that's informative, the posterior is going to shrink a lot. And so the entropy here is going to be a lot smaller than what you had at the beginning. So this change in entropy is a measure of how much you learned. And so I'm going to scan over all the experiments that I might do and try to find the one that's going to, that in expectation, assuming my model is going to, maximize the expected information gain. Is that fine? Okay, so this is going to be the setup. Again, the only way that I could do this is if I have a model for what the data would look like, right? You can't answer this question ahead of time. You don't have the data yet, right? You're trying to imagine experiments that you could do. And if you were to do them, you need to be able to predict what the data would look like under, if you make some assumption about what the parameters of nature are. And so this already really goes back to, a lot of the themes and Pearl's talk, right? This is not something you can answer if you just know a big joint distribution over the data, right? This is a question of what would the data look like if I were to perform the following experiment, right? So this requires a causal generative model for what's going on. And so that's one of the things that somehow as a physicist, I both knew and was completely not aware of simultaneously, is that physical theories are not, I kind of thought about Feynman diagrams as a distribution, just encoding a distribution over the data, and they do, but they encode a distribution over the data coupled with whatever experiment that I'm doing, right? So they're a much more powerful thing. The theories in general, they make predictions in a context, and figuring out how to tie those two things together is interesting, but they're really all the theories are basically constant. Okay, so if this is my goal, this is what I want to optimize, say for the purpose of this talk, you could, pick something else, but then this is kind of my scientific loop and sort of workflow land, right? So I'm going to start off with some experimental configuration. I'm going to perform an experiment. So that's this block is doing an experiment. I get some observed data. I'm going to put it into my inference machine. It's going to take the data and my prior, do Bayes and stick out a posterior. Okay, and then I'm going to. So now I have a new posterior, and then I want to figure out what experiment to do next. So at this point, I need to go make proposals over possible experiments that I might do, evaluate the expected information gain for each of them, keep doing that until some sort of convergence, and I'm happy with what I think is the experiment that's going to optimize this, and then I stick it up into the loop, I have a new experimental configuration, I sit in the loop, right? So, and then this expected information gain, block here, this one thing, what is it, right? I start off with some experimental configuration. I need to imagine what the data would look like. So I run a whole bunch of simulations. I take my simulated data instead of real data. I do the base stuff. I get a posterior. I calculate the information gain between the prior and my posterior. Do that many, many times with to get an expectation and try and then at some point I'm happy with my expected information gain calculation. I spit it out. So this block is like what's happening just here, right? So you can just, from an engineering mindset, you can just start building all of this. And I did build all this, and I'll show you these things. But at this point, again, like Bayes just happens, and this is kind of like, you're probably just thinking symbolically Bayes theorem here, right? But that, of course, can be a heavyweight operation sometimes. Okay, so, all right, now let's talk about the ingredients to do this. So if I want to do this argmax, okay, I'm sorry, this is a break-in notation because I borrowed a slide from this. And X here is really meant to be like the deltas, like what experiment am I going to do next? Or I guess A, actually, the action that I'm going to take. So I want to do this maximization. That can be very costly. So I'm going to bring together these sort of three ideas in this next little bit. So one is the idea of active learning. Another one is like a kind of engineering issue, which is about reproducible workflows or reusable workflows. And then later we'll get to simulation-based or likelihood-free inference engines. Okay, so the first part, let's talk about active learning. Some other people have talked about this in previous talks, so I'm going to go quickly. But the basic idea is this axis is supposed to be what experiment I might do. And this vertical axis is the expected information gain. I don't know this function ahead of time, so I have to go calculate it, which is expensive. So these red dots are supposed to be like evaluations of this unknown function, and the red dotted line is supposed to be like the true underlying function that I don't know. Okay, and it's noisy. I get noisy estimates. So I go evaluate it a few times, and then I can use a Gaussian process to try to approximate what this underlying true unknown function is. And so that's the dotted green line based on these data points. It basically goes through the green data, the red data points. It has uncertainty bands around it. So between the points that I've evaluated it, the uncertainty is large. And now I need to figure out, I'm trying to maximize this function. I could just sort of go to the top of this green line. That's my best guess of the maximum, the maximum of the function. But there are these other areas where I have a lot of uncertainty, right? So there's this trade-off between exploration and exploitation. And so there's various ways to deal with that. And so you pick one of the different ways of trading this off. So one of them would be basically to look at the upper confidence band, like the top of this green envelope. Yeah. This confidence band is this is like ridge regression or Gaussian processes. So you basically imagine that there's a function. It's like there's a function here, and at every point it's like a Gaussian distribution here, but there's like a covariance between nearby points to give you smoothness. So you have to, So you have a modeling choice, which is what level of smoothness do you think is there, and you can try to update that as you get more data. So I'm kind of sweeping that part of the rug. If you didn't assume anything, it could be anywhere. But if you think there's some smoothness, then it's going to look roughly like this. Yeah. If I do that, so here this blue curve is some kind of what's called an acquisition function, which is the trade-off between exploration and exploitation. And this is basically saying how valuable do I think it is going to be to run my simulator at all these different points. That's a cheap objective. I go optimize that thing. I find the blue point. I say I should go run my simulator there. I run my simulation there. I calculate this expected information gain. It sits somewhere on the true, this unknown red function, but now I've evaluated it. I update my Gaussian, process to this green thing, and I have, a new guess, and I just keep iterating this whole process. And then at some point, it basically converges, and I'm like, okay, I'm pretty sure this looks like the best guess to optimize this function. So that was like a quick surrogate. Like I only evaluated the expensive thing 1, 2, 3, 4, 5, 6, 7 times, but then I have a pretty good guess for where the optimum is. So this is this Bayesian optimization approach. Yeah.
That is like it's trying to learn the distribution of that. So that's what we said that's acceptance and the rejection process. Okay.